All right, so this is the first formally new lesson in this course. The first chapter of this course is about transformations. And we've already looked at a lot of these things informally with quadratics, and the main idea is we're going to move away from just quadratics. But I want to start with the graph of what I'm calling g of x, which is the absolute value of x. Now, you may or may not have learned about absolute value before. So we'll say these brackets you see around the x, though they are brackets, they affect the order of operations, but they're not just any brackets. What they do is, in effect, whatever value you have inside the brackets, these absolute value brackets, becomes positive. So for example, if I just kind of slide over here, if I ask you what's the absolute value of 3 minus 5, well, they're brackets, so first order of operations, do what's inside the brackets. 3 take away 5 is negative 2. So that's the same as the absolute value of negative 2. And the absolute value of negative 2 is positive 2. Whatever is inside the brackets. And once you've evaluated everything, it makes everything inside it become positive. But first, they are brackets. So 3 take away 5 is negative 2. Absolute value of negative 2 is 2. If, let's say, I had the absolute value of minus 3 minus 5, again, order of operations, first, I have to think, what is negative 3 take away 5? Negative 3 take away 5 is negative 8. The absolute value of negative 8 is positive 8. Essentially, all it does is switch the sign. But notice, if you're tempted to start switching the signs right here, like start switching these things around, you'll almost always get a wrong answer. Because again, you're not really following order of operations. Again, now what if I have something that's all positive? What if I have the absolute value of 3 plus 5? Well, that's the same as the absolute value of 8, which is just 8. So the absolute value of any number, I don't know, pick a number, 6. The absolute value of 6 is 6. The absolute value of negative 6 is is positive 6. Get a little carried away there. So when dealing with just numbers, absolute value is really, really simple. Effectively, they're brackets, and if everything inside the brackets ends up equaling a negative number, it's now positive. If everything inside the brackets ends up equaling a positive number, it stays positive. Okay, so what does the graph of this look like? What's the graph of the absolute value of x look like? Well, anytime you're not sure what a graph of something looks like, it's not a bad idea to make a table. So of x and absolute value of x, or y. So pick a number, 0. The absolute value of 0 is 0. So this graph will go through 0, 0. Okay, what about 1? The absolute value of 1 is 1. The absolute value of 2 is 2. And you get the idea. The absolute value of 3 is 3. So if x is positive, the absolute value of it is the exact same thing. And y is the same. So notice all these points I've drawn, the y coordinate is the exact same as the x coordinate. However, what if x is negative? Negative 1. Well, the absolute value of negative 1 is positive 1. So when x is negative 1, y is positive 1. And when x is negative 2, y is positive 2. When x is negative 3, y is positive 3, and so on. And so if you create a table of values, you quickly realize the absolute value of x makes this V shape, where when x is positive, x and y coordinates are identical. When x is negative, the y coordinate is still positive. And so again, keep in mind, this graph is not just a bunch of points. It's a solid, continuous function that goes on forever. All right, so what I have there is the graph of the absolute value of x, which I'm calling here is g of x. OK, let me erase this table now. And again, you may have learned about absolute value in pre-calc 11. You may have not. Normally, I do teach it, but if I taught you during the spring, I had to cut it out. So again, that's a very quick, not very thorough version of what absolute value is. But for right now, the most important thing is that the absolute value of x looks like this V shape. It's actually a pretty simple graph. OK, so what I want to do here? Well, it says for each of these equations down here, sketch the graph as well as write the equation in terms of x and y only. So if I look at the first one, I've already graphed g of x. G of x is the absolute value of x. So I've already made the graph. But what's the equation? It also says write the equation in terms of x and y only. Well, if you look right here, that is an equation, but it's in terms of x and y and g. And so this equation here relies on looking back up to this step right here. What is g? G is the absolute value of x. So this equation that, again, I have already is the equation of this function in terms of x and g. I want just x, or x and y. And so in this case, it's quite easy, because g of x, I've already stated, is the exact same as the absolute value of x. And so if I write y equals the absolute value of x, that's the equation in terms of just x and y. Whereas this is the equation in terms of x and y and g. Or another way of looking at it, if I ask you to graph this, y equals g of x, you can't do that. You don't know what, you can't do that unless you look up here and you reference what g of x is. Whereas if I just ask you to graph this, you can do that. You don't, it doesn't refer to something else. All right? So long story short, this is what we see. This is the equation, the explicit equation. This is the graph. OK, so next, I have g of x take away 4. Let me do the equation first. So it's g of x, which is the absolute value of x, take away 4. And the key is the 4 is outside of the brackets, because if I look right here, this take away 4 is outside g of x. It's not inside the brackets there. And so the equation is the absolute value of x take away 4. So what does that look like? Well, perhaps you can guess from quadratics that this is going to be identical to the graph we already have, except it's moved down 2. Where is that coming from? Down 4. And so all I need to do is take that v, that absolute value of x I sketched, and translate it 4 units down. And I will have then the graph of g of x minus 4, or the graph of the absolute value of x take away 4. And so again, this is the absolute value of x. Let me pick, I don't know, purple. And so I'll start with this sort of center point right here, and it's now 4 units down. And I can just take any of these points and draw them 4 units down. And really, though, once I draw a few, I don't think I need to draw any more. I'll just grab a ruler. And there is my graph of not g of x. This is g of x take away 4. Or this is the graph of the absolute value of x take away 4. OK, so again, we want to be clear about what's the actual equation. The actual equation for what I just drew is the absolute value of x all take away 4. And there's the graph I've drawn in purple. OK, let's look at the next one here. So now I have g of x minus 4, but the minus 4 is inside the brackets. Compare how this is different from the last one. So in this case, that take away 4 you see there is all inside function g. If I look back up here, function g is the absolute value of x. So this kind of comes back to the very first review lesson we had, where in this case, the take away 4 is inside the function, and g of x is a pretty simple function. G of x finds the absolute value of whatever you put inside it. In this case, I'm putting inside x take away 4, so it's the absolute value of x take away 4. And notice the difference between this and the previous one. In this example I have right now, take away 4 is inside the function, and so the equation, it's inside the absolute value. Up here, take away 4 was outside of the function, so it's outside of the absolute value. All right? When you say them out loud, it may seem like they're the same. That's why generally this one right here, we would say the absolute value of x, all take away 4. Here we'd say the absolute value of x take away 4. Either way, it's easier to just have it written down than to say things out loud in this case. So what does this look like? Well, perhaps you can guess that this is going to be the exact same as the first graph, but I'm subtracting from the x. So with quadratics, when you subtract from the x, it moves to the right, and that's the same thing for all functions. So this is going to look the exact same thing. It's going to look congruent to what I drew for the first example, but moved 4 to the right. And so let me look back to my first example, the one in green. That's the absolute value of x. And it's going to look congruent to this, but everything's going to be 4 units to the right. So it's going to look something like this. And I'll grab my ruler. And so this is the equation for g of x minus 4, or the absolute value of x minus 4. And so The main thing is to realize the difference between these last two examples, where I'm subtracting 4 from inside the function or subtracting 4 from outside the function. And hopefully that sounds kind of familiar because it's the exact same thing we saw with quadratics. All right. So lastly, combining a few things together, the equation for this would be the absolute value of x plus 3, because x plus 3 is inside the function. So in this case, it's going to be inside the absolute value. And the plus 5 is separate, so the plus 5 should be out here. So compared to what I graphed at first, I should have something that is 3 to the left and 5 units up. So again, I'm going to go back to the first thing I drew, which was that absolute value of x, and I'm going to move it, I'm going to translate it 3 units to the left and 5 units up, and then I'll be done. So this point here, I'm going to move 3 to the left, 5 up, and now it's right here. And then all the rest should be easy to draw, and there's my sketch. All right, so before we go on to the next page, let me just switch to something here in Desmos. Really the same thing here. And so what you see as a dashed line here, this is the absolute value of x, or if you look at my equation right here, g of x. If I turn this on, what you see in green is the exact same thing right now, because if you look for this equation in green, it's g of x plus k. But if you look up to my slider, k right now is 0. And so if I add a positive number, if I make it a bigger number, let's say I make k 4, now I have the exact same graph I gave you at first, but moved 4 units up. If I make it 10, it's the exact same graph, except 10 units up. If I make k negative 5, it's the congruent to the original graph, but 5 units down. And if I just let this change on its own, right, as k is positive, it moves up. As k is negative, the whole thing moves down. Exact same thing with quadratics. It's pretty straightforward that way. The more you understood quadratic transformations, the easier this is. The less you understood it, the harder this is. And so, same thing, same idea as we saw with quadratics, if I add or subtract a number inside the brackets. And so h right here, if I turn this on, there we go. Notice right now what you see in black is congruent to g of x, but 2 units to the right. And that's because if you look at the top, h is negative 2. So I'm adding negative 2 to the x. Adding negative 2, same as subtracting 2. Anytime you're subtracting from the x, it's moving to the right. And the more negative I make this, the more it moves to the right. Once h becomes positive, once I'm adding a number to x, it actually moves to the left. And if I just let it go by itself, notice anytime h is negative, the graph is on the right of where the absolute value of x is. Anytime h is positive, it's the other way around. And again, no differences in ideas between this and with quadratics. So let me pause that, and let's get back to this. All right. So next, I want to introduce something that is probably new, but it's actually pretty straightforward. We call mapping notation. It's another way of describing a transformation without words. So for example, for each of these, I want to describe the transformation compared to f of x in words and using mapping notation. And again, that mapping notation, which I'll get to in a moment, is I expect to be new. So first, I'm saying how all these compare to f of x. Well, what is f of x? I don't know. I don't care. It doesn't actually matter. F of x is some function. It could be an absolute value function. It could be a line, a quadratic. It does not matter. What matters is that if I have f of x and then I add 5 to the x, I don't care what the function looks like. This is going to take that original function, whatever it is, and it's going to move it 5 to the left. So that's a transformation in words. So whatever f of x looked like, f of x plus 5 will be congruent to it. It will be the exact same shape, but move 5 to the left. So how do I show that in mapping notation? Well, mapping notation would look like this. First, I start with, in brackets, x comma y, and an arrow. So this is saying x comma y represents the coordinates, an x coordinate and y coordinate, of some point on f of x. Well, when I move it 5 to the left, the y coordinate doesn't change. The x coordinate has 5 subtracted from it. And so what you see here is mapping notation. It's a way of expressing a transformation without having any words. And I have nothing against words. I'm using lots of words right now, but this is just another way of expressing it. And ideally, what I've highlighted in green, you don't have to understand any English for that to make sense, whereas the rest of it you do. All right, so what you see in green is mapping notation. What I have in red is the description in words. They're saying the same thing, though. So next, for f of x minus 2 plus 3, let me first express the transformations. When I subtract 2 from the x, that is 2 to the right. And when I add 3 outside of the function, that is 3 up. So what does this look like in mapping notation? Well, it always starts with x comma y, which just represents some point on f of x. But now if I subtract 2 from the x and add 3 to the whole thing, well, my x coordinate, whatever I look at, will move 2 to the right. So if you move 2 to the right, you add 2 to the x coordinate. And my y coordinate, wherever it was, is going to move 3 up. So it's y plus 3. And that's in mapping notation. Lastly, same idea here. I want to first express these transformations in words. What I'd like to do first is actually add 2 to both sides to rewrite my equation in a more convenient form. And so for this, I'm going to write it as f of x minus 1 plus 2. Equivalent equation to what I have before, but it's in a more convenient sort of form. So now I can see these transformations more clearly. This minus 1 right here represents 1 to the right. And this plus 2 represents 2 up. Again, there's nothing, the form I have up here is not inherently wrong, but it's easy to misread if you don't put it into this sort of more familiar form, if you don't add 2 to both sides, or in this case, solve for y. All right, and now in mapping notation, what would this look like? Well, x comma y maps onto, we say. Well, if I'm moving 1 to the right, that means my x coordinate is going to have 1 added to it. If I'm moving 2 up, my y coordinate, wherever it is, will be 2 more, and that's in mapping notation. But keep in mind that and this represent the same thing. All right, so let's kind of generalize and summarize what we have here. For any function f of x, again, really, the only difference between this and what you did in quadratics is that in quadratics, you may have thought that everything you learned about transformations only worked with parabolas, but now it is the same for any function. And so for any function, if you add a number to it, well, that represents what we call a vertical translation. Up or down, using less fancy words. Okay, we call that a vertical translation. But, you know, if that k value is positive, then it's going up. If that k value is negative, then it's going down. But more importantly than these words here is just to have this sort of sense, a gut sense that when you take a function and you see an equation where you just suddenly add a number to it, the graph is going to look identical to what you had before, but it's going to move up some amount. And if you subtract, it's going to move down. And I can also express this in mapping notation. So in mapping notation, I can say it like this. It's very succinct. It's very to the point. I can say x comma y maps onto x comma y plus k. Again, if we just take a function and we add some number to it, the x coordinates will never change. It doesn't move left or right. It only moves up or down. Hence, if you see in mapping notation, the x coordinate hasn't changed at all. OK, the x coordinate changes, like in the next example, if we add something or subtract something from the x, from the input. Remember, x represents the input of a function. And so in this case, as soon as you add or subtract something inside the function, this is a horizontal translation. And it's kind of how it works is the reverse of what we saw before. If h is a positive number, if you're adding something, then it moves to the left. If h is a negative number, if you're subtracting from x, it moves to the right. And again, fairly straightforward idea if we looked at this thoroughly with quadratics in pre-calc 11. And I can summarize this in mapping notation. Always starts with just x comma y, the arrow, which we say it maps onto. In this case, if I'm adding h, notice if I look at my expression here, I'm adding h right here. If I'm adding h, I'm actually going to subtract h from the x coordinate, but my y coordinate won't change. All right, so mapping notation really algebraically shows you how to move the coordinates if you think of them as ordered pairs, whereas words describes the same thing in words. It's all the same thing. Okay, if one makes more sense than something else, fair enough. Ideally, they all eventually are interchangeable to you. Right, so the final problem is looking at, I think just this one question, where I have what we call a sine wave. So what we see in blue is the graph of the sine of x. Honestly, the equation doesn't matter. just that what you see in blue is the sine of x, okay? Why it makes a wave, we'll learn about later on in the course. What I want us to do is a few things based on that. So first, on that same grid, I want us to make a graph of the sine of x take away 1. So what does that, what's the difference between that and the sine of x? Well, there's just that take away 1. So first we've got to realize the take away 1 you see there is not inside the sine function, right? What we have right here is not the same as this, right? These are different. For this example here, 1's being subtracted from the x, from the input. What I want us to work out is where 1 is being subtracted from the whole function. And so once we realize the difference there, hopefully we feel pretty good that what we have here is 1 down. So the sine of x minus 1 is going to look identical or congruent to the graph of sine x, which is shown as a dashed curve here, but moved 1 unit down. So I'm going to draw that, but I'm going to make a mistake. Okay, so if you visualize this now, and again, the sine of x, maybe I'll highlight this one in yellow. Right, the sine of x is right here. So I want to take this, I want to visualize this wave, which again, we'll understand later on in the course why it looks the way it does. I want to visualize it translated 1 unit down. So if you do that and you visualize something like this, unfortunately, I won't say unfortunately, well, we're wrong. It's good to make a mistake. I only say unfortunately, unless we are so certain we're right, but this is wrong. So what's wrong here? I didn't move this 1 down. If I look at the scale of my graph, I moved it 1 grid line down. But if you look at the scale, this is 0.8, this is 0.6, this is 0.4, this is 0.2. What I've sketched in red is the sine of x take away 0.2. I want take away 1. So I can't just count grid lines in this case. I have to pay attention to the scale of the graph. And so once I realize that, I go, okay, I want to take any point. I'll start with this point right here, okay, at 0, 0. And if I move that 1 down, it's now right here. And once I realize that, it's pretty easy to draw the rest of it. This point right here on the sine of x, I want to move it 1 whole unit down, which is right there. Again, 1 unit in this case is 5 grid lines. Anytime you have a graph, you always have to pay attention to the scale of the graph. Notice my x-axis is going up in fractions of pi. So I mean, you can't just ignore the scale of the graph. But once we realize that, I can draw this pretty quickly. This point here on sine of x, move it a whole unit down. It's down here. This point here on my graph, move it a whole unit down. It goes off my grid a bit, so I'll kind of estimate it right here. And I have something like this I'll draw. And I'll put little arrows on this, and so on. Okay, so what I've sketched in red is the graph of sine x, all take away 1. All right, so the last question is to look at the graph in green, and let's figure out the equation of the graph in green. All right, so to figure out the equation of the graph in green, I need to think about how does it compare to the graph in blue. Now for this, I'm actually going to erase my graph in red just because I don't want to be distracted by it. But you probably don't want to erase it for your notes. But how is the graph in blue compared to the graph in green? Well, let me look at these 3 points I've already kind of plotted here. So this point here, I can see, definitely corresponds with this point right here. So, it's moving, I can see 1 square down and 1, actually I'll draw it a little differently. It's pretty clear to me that it's moving 1 square down and 1 square to the left. But what are these squares? Well, I've already kind of mentioned that on the vertical axis, each grid line I can see represents 0.2. So I can see that to go from blue to green, it's moving down 0.2, or 1/5. 0.2 and 1/5 of this are equivalent. What about to the left and the right? How far is this right here? Again, it's 1 grid line to the left, but what's a grid line? Well, let's look at my x-axis. From here to here is pi, right? That's a pi symbol right there, which means each of these grid lines must be a 1/4 pi, because these grid lines break up pi into 1, 2, 3, 4 equal pieces. which means the distance from here to here must be 1/4 pi. And so each of these grid lines is 1/4 of a pi, or pi divided by 4. And that's all I really need. This is moving 1/5 of a unit down and 1/4 of a pi, pi divided by 4, to the left. And so that's all I need. I now know if I were to say this in words, I would say that the graph of what you see in green is congruent to the sine of x, but translated 1/5 of a unit down and 1/4 pi to the left. But the question asks for the equation. So how do I put that into the equation? Well, I can say equals the sine of x plus pi over 4, right? Because I want to move this graph 1/4 pi to the left. If I want to move anything to the left, I have to add. And minus 1/5, or 0.2, out here. And so if I type, in fact, this right here is what I actually typed into Desmos to create the graph you see here. Now again, if you are tempted to go to your calculator and decimalize pi over 4, you get some decimal that's not as accurate as pi over 4, plus it's more work, so don't. Just pi over 4 is great. And again, whether you have 0.2 or 1/5, they're both perfectly good. They're both just as accurate. I'm going to go with 1/5 just because why not? All right. With that said, though, I'll make one last comment. How do you know that this is the transformation and not this? How do you know this graph didn't go 0.2 units down and all the way to here? All right, if you take that graph in blue, the sine of x, if you move it 1/5 down and then all the way this long orange arrow to this point here, it would also create the exact same wave you see in green. So how do you know that didn't happen? Well, we don't know. That could have happened, which means this is not the only correct answer. This is the simplest correct answer, so it's the only one I'm going to write down, but there are actually an infinite number of other correct answers if you imagine it going different ways, or if you imagine it going this way, going a fifth of a unit down, and then that way. What I showed you initially is what I think is the simplest, but there are countless correct possibilities. All right, so before I end this, keep in mind the homework for this you have already, but I'll still write it down this time. So this is from your textbook, so not from the Pre-Calculus 11 textbook. Remember, the homework is broken up into different sort of difficulties. And just like any other textbook you've had in a math course recently, regardless of how confident you are with this, there are intended to be some fairly straightforward questions, but maybe not. And there's definitely intended to be some very, very challenging questions. So you don't really know how well you understand this till you try a variety of things. That's what homework really is. Homework is about a way for you to check your understanding of things. And if you don't know how well you understand this topic if you just view the notes and try a couple homework questions, because you don't really know till you try a variety of things. All right, so that's the whole purpose of the homework, and I'll stop it there.